Hello all! Welcome back to the Knowledge Tower, where we investigate the science behind the Bionicle legend. In the last edition of the Knowledge Tower, we reviewed possible sizes of the three bodies within the Spherus Magna system, using the canon size of the Great Spirit robot as a measuring stick. In that video, we concluded that, if we stuck purely to canon numbers, Spherus Magna would wind up being several times larger than Jupiter, the largest planet in our solar system and a gas giant. This was not a realistic size for a terrestrial planet like Spherus Magna, and reducing our measuring stick to the smaller size GSR from Christian Faber didn't really help either, with the resulting sizes still being far too big to fit with current theories on terrestrial planet size limits. Ultimately, this led to a Knowledge Tower approved size estimate that worked backwards from the limits imposed by science, one that not only fit within those limitations but was also aligned with at least the Faber GSR, though not the canon one. The final sizes within that Knowledge Tower approved estimate were Bara Magna, and originally Spherus Magna, were 1.7 times larger than the Earth, Bota Magna was 1.41 times larger than the Earth's moon, and Aqua Magna was about 0.95 times the size of Earth's moon. While that video concluded that these were realistic in terms of size alone, a comment from user Zeglador quite rightly pointed out that for supposedly habitable worlds like these, the sizes for Bota Magna and Aqua Magna in this version might actually be too small to fit with the science. The reason for that all has to do with one key point that wasn't covered last time: their atmospheres. In this video, we will be exploring why retaining a habitable atmosphere may be a problem for these moons, just how big of a problem this may be, and, ultimately, if this Knowledge Tower approved size estimate is actually possible after all. First off, let's take a look at the background of the problem that Zeglador raised. The atmospheres of bodies in space are held in place via gravitational attraction from the body itself. Therefore, the smaller and less massive something is, the harder it is for it to hold onto an atmosphere. This is all due to the escape velocity of the body. Escape velocity is the minimum speed needed for an object to escape from the surface or orbit of a body in space. It's a term you've probably heard about before when talking about real-world space travel. For example, here on Earth, a rocket needs to reach a minimum speed of 11 kilometers per second if it wants to escape the gravitational pull of the Earth and explore the wider solar system. But this doesn't just apply to rockets, it applies to anything leaving the Earth. If it has a speed of 11 kilometers per second or above, it can leave the Earth and escape into space. If not, it will be pulled back in by Earth's gravity. In terms of the atmospheres of planets and moons, this is also the way that they can lose those atmospheres over time. If air molecules gain enough kinetic energy to reach or exceed the escape velocity, they will be lost into space, and their atmospheres will thin and eventually disappear altogether. This kinetic energy can be imparted to the air molecules in four main ways. The first is thermal escape at the molecular level, also known as Jeans escape. This is where individual molecules are heated sufficiently to gain the additional energy they need to achieve escape velocity. The second method is known as thermal escape at the bulk level, also known as hydrodynamic escape. This is where a large amount of thermal energy is absorbed by the atmosphere from space, for example via ultraviolet radiation, which causes the atmosphere to expand, with that expansion accelerating the air molecules in the upper atmosphere until they reach escape velocity. The third method is non-thermal escape. This is where effects such as collisions with charged particles from the solar wind can impart the energy needed. And the fourth is impact erosion, which is where a large impact with the planet from a meteoroid or other such body can impart enough kinetic energy to the ejector from the impact to achieve that escape velocity. As a quick aside, non-thermal escape is an especially pronounced effect for planets that don't have magnetic fields or have lost them over time, and so no longer have that protection against the solar wind. This is one of the primary theories for how Mars lost the much thicker atmosphere it's thought to have had billions of years ago. For lighter elements, such as hydrogen or helium, only a small amount of energy is needed to be imparted to them to achieve that escape velocity, while heavier elements, such as nitrogen or oxygen, require more energy to achieve that velocity, as they have more mass, and therefore need a larger force to accelerate them to that same speed. In terms of the Earth, the escape velocity is high enough that it is very rare for nitrogen or oxygen to have sufficient speed to escape the planet, whereas hydrogen or helium are light enough that they are regularly lost to space. That is why there is so little of those lighter elements in our atmosphere, and why the heavier elements are in such abundance. And it's a good thing too, given that oxygen retention is a key requirement for the continued existence of life on Earth. What all of this ultimately means is, the smaller the size and mass of a body in space, the lower its escape velocity, and therefore the easier it is for gases in its atmosphere to escape, even the more massive ones that are required to keep an atmosphere habitable. So, the question is, given we have put the size ranges of Aqua and Bota Magna to being roughly similar to that of our Moon, would they be massive enough to be able to hold on to the required gases to keep their atmospheres habitable? Well, to know that, we need to work out their mass and then use that to determine their gravity and escape velocity. We already know the diameters of each world, and from that it's easy to work out their volumes too, simply by using the equation for the volume of a sphere. This does get a bit more complicated for Magna, given it has two enormous craters in it, but we will ignore that for now, as we are concentrating on Aqua Magna and Bota Magna here. Once we have the volume of both bodies, we can find the mass by multiplying their volumes by their densities. Then, once you have the mass, you can use these equations to work out both the acceleration due to gravity and escape velocity. Here we run into a new problem. We don't actually know the density of the moons. There are potential ways around this issue, however they would involve enough additional calculations to be the subject of a video on their own. So, for now, let's just sub in the average density of the Earth for each body to get ourselves a baseline measurement. The average density of the Earth is 5,515 kilograms per meter cubed. Alongside our sizes from the last video, we can use this and the equations shown before to work out what we need for each of the three bodies within this Knowledge Tower approved version of the system. Doing that, Spherus Magna has a pre-shattering mass of around 2.94 times 10 to the 25 kilograms, or around 4.93 times the mass of the Earth. That gives it a surface gravity of 16.71 meters per second squared, or around 1.7 times that of the Earth. It also gives it an escape velocity of 19 kilometers per second, also around 1.7 times faster than that of the Earth. Bota Magna post-shattering ends up with a mass of around 3.39 times 10 to the 23 kilograms, or only around 0.06 times that of the Earth. Its surface gravity is therefore only 3.77 meters per second squared, and it has an escape velocity of 4.3 kilometers per second, both around 0.38 times that of the Earth. Post-shattering Aqua Magna, meanwhile, has a mass of around 1.05 times 10 to the 23 kilograms, only 0.02 times that of the Earth. With that low mass, we get a surface gravity of 2.55 meters per second squared, and an escape velocity of 2.9 kilometers squared, both around 0.26 times that of the Earth. Post-shattering Magna is a bit trickier due to those aforementioned massive craters, but if we take the mass of Spherus Magna pre-shattering and remove the masses of Aqua Magna and Bota Magna, we can get an idea of the average across the planet. Doing that, post-shattering Magna gets a mass of 2.9 times 10 to the 25 kilograms, a surface gravity of 16.45 meters per second squared, and an escape velocity of 18.89 kilometers per second. Surprisingly, not actually all that different from pre-shattering Spherus Magna. This actually tells us something that is not all that intuitive, but makes sense with the numbers and measurements that we have made. Whilst the shattering was undeniably disastrous, Aqua Magna and Bota Magna are actually pretty small on a planetary scale, and by this measure their loss only accounted for a reduction of around 1.5% of Spherus Magna's original mass. So, how do these masses and escape velocities relate to the prospect of atmospheric loss that we covered earlier? Well, for that, my research uncovered this very cool graph. The y-axis of this graph shows a range of escape velocities in kilometers per second, while the x-axis of the graph shows a range of temperatures in degrees Kelvin. Each band within the graph represents the temperature range within which several key gases will have insufficient energy to escape a body with that escape velocity. What I find really cool about this graph is not only the escape point data itself, but also the fact that it shows where all the significant bodies within our solar system exist within this this data. The planets and moons are represented to scale here, with their actual data point being the black dot in their centres. I know it's incredibly nerdy, even for me, but I really love this graph, and we can use it alongside the escape velocities determined from earlier to see where the knowledge tower sizes fit. Given temperature is another key factor for habitability, we will draw a line here on the x-axis that cuts through the same temperature as the Earth, to ensure that our measures will keep the Spherus Magna system bodies within the habitable temperature range. Again, similar to Earth, we will want our results to fall within this zone, where we keep all of our key gases for habitability, but can lose others like hydrogen and helium. Plotting them on the graph, we see that Spherus Magna and post-shattering Bara Magna fall within our desired range, easily holding on to key gases like water vapour, oxygen, nitrogen, and even holding on to lighter elements than the Earth can, with them lying on the dividing line for helium and hydrogen. This makes sense given the parameters we set in the last video, with the sizes being at the top end of what is possible before gravity becomes strong enough to draw in the lighter gases and become a gas giant rather than a terrestrial planet. So far, so good. But, as you have probably already guessed, the problems lie with Bota Magna, which lies here on the graph, and Aqua Magna, which lies all the way down here. In this model, Bota Magna would be able to hold on to carbon dioxide, but all of that life-giving oxygen would escape into space. Aqua Magna fares even worse, with the only gas on this graph it's massive enough to hold on to being xenon. Well, that's a bit of a letdown, isn't it? The last video proved that these bodies are the sizes that they must be to fit with their relative sizes to Bara Magna, and Bara Magna is the largest it could possibly be to fit with the current theories of planetary formation. So, does that mean that there is no version of the Spherus Magna system that can fit with the physics after all? I'll admit, when I came to this conclusion, I was quite disappointed, but I wasn't ready to call it quits quite yet. Instead, I decided to approach it from the opposite direction. If I could use the graph again to find out what the minimum escape velocity can be for a body to be able to hold on to a habitable atmosphere, I could then use the size data to work backwards to find the mass and density that would be required to produce that escape velocity. If the resulting mass and density measures were at least possible, if not necessarily reasonable, then I would still call it a win. Going back to the graph, to be as generous as possible, we will look just above this threshold here, where the body could definitely still hold on to its nitrogen and oxygen no problem, but where it's at the lower end of what's possible to hold on to its water vapour. I do want to stress that in this scenario, it is still within range for where it would be large enough to hold on to that water vapour, but it's at the lower end of that scale in order to give these smaller sizes their best chance. Keeping to our temperature line and checking the escape velocity on the y-axis, the lowest we can reasonably go here is 7 km per second. Any lower and we are in real risk of the body being too small to hold on to its atmospheric water vapour. Plugging that figure into our equations as the escape velocity and working backwards, Aqua Magna, the smallest of the three, would need to have a mass of 6.08 times 10 to the 23 kilograms, or around 10% that of the Earth. Unfortunately, to pack that much mass into a volume smaller than that of our moon, like we calculated for Aqua Magna, we would need to have a truly absurd average density of 31,937.66 kilograms per meter cubed. Not only is that 5.79 times denser than the Earth, but it is also 1.42 times denser than osmium, which is the densest natural element at 22,570 kilograms per meter cubed. So that's another strike against habitability at these sizes. Discouraged, but still limping on, I decided to look into one last factor. If we assume the Earth density from before, and that the circumstances of the shattering allowed the moons to keep their share of the original habitable atmosphere, over what timescale would they lose it? While the 100,000-year existence of these moons between the shattering and the reformation seems unimaginably long on a human timescale, geologically speaking, it's really just the blink of an eye. If these mechanisms of atmospheric loss occur over millions of years rather than thousands, then they may still have retained their habitability until the reformation of the planet. As we have already discussed, non-thermal escape via the solar wind can certainly strip an atmosphere, just like it did with Mars. According to my research, an unprotected atmosphere at the Earth's distance from the Sun could lose up to 1 billion kilograms per year in this way. We don't know if Aqua Magna and Bota Magna have magnetic fields to protect them, but even if they don't, this would still not really be a factor. While 1 billion kilograms a year is a massive amount, compared to a full atmosphere, it's actually not that much. Earth, for example, has an atmospheric mass of around 5.5 quintillion kilograms. If we say that the atmosphere of Aqua Magna is only 0.02% that of the Earth's to keep in line with the mass comparison from before, that's still 110 quadrillion kilograms, something that would take the solar wind 110 million years to strip away. That's a bit more encouraging, but it's really thermal escape and hydrodynamic escape that we really need to worry about. And for that, we need to bring out another cool graph. This one shows the number of years it would take for a body to lose 10% of its atmosphere via these mechanisms on the y-axis, and the ratio between the body's escape velocity and the average velocity of the molecules in its atmosphere on the x-axis. The black line on this graph represents loss via hydrodynamic escape, whereas the green represents thermal escape. So, where do our key habitable gases lie on this graph for Aqua Magna? It's the smallest of the two moons, so if it can keep more than 90% of its atmosphere in that 100,000 year time period, then so can Bota Magna. To work out the average velocities of air molecules, we can use this equation, with the temperature being set at 300 Kelvin to match with the temperature we are working with from the first graph. For our key gases for habitability, that gives us the velocities you can see in this table. Using our escape velocity for Aqua Magna from earlier, that puts them here on the graph. As you can see, it would take over 1 billion years for approximately 10% of the nitrogen, oxygen and carbon dioxide to be lost to space. That's more than enough time for our 100,000 year habitability requirement. Water vapour, however, is still a bit of a problem, losing 10% of atmospheric water vapour in only 10,000 years. But then again, if it is similar to Earth, then only 0.001% of the total water on Aqua Magna would be within its atmosphere. This could therefore be easily replenished via evaporation from the endless ocean without noticeably affecting the sea level during that full 100,000 years. So I think this is a point towards habitability also. The figures for Bota Magna are even more encouraging, with it being massive enough to take over 1 billion years to lose 10% of all its key gases, including water vapour. Which is certainly good for that world, as it doesn't have a vast ocean to replenish its lost water like Aqua Magna does. So, in the end, could the more realistic Knowledge Tower approved sizes for these bodies really allow them to remain habitable? It took us a while to get there, but I'm happy to say that the evidence really does suggest so, at least for that 100,000 year timescale that we need. Thanks again to Zeglador for the peer review comment that started all this. I had so much fun and learned so many new things in the making of this video, and I hope you all had fun watching it too. Are there any of my previous videos you would like a deeper dive on? What areas of the Bionicle lore should I look into next? Let me know in the comments, and I will see you again soon for another Bionicle Science investigation here at the Knowledge Tower.